Okay, in this second video, we're just going to do some couple of calculations of interest, and actually we're going to calculate the amount an investment is worth if you invest a certain principal P at an interest rate R given in decimal, or with a particular compounding schedule where N is the number of compounding periods per year, and then for a number of years where T is the number of years that the money is invested. And let me show you a little chart that you can write for N, so you'll know what the values of N would be in certain situations. So given a certain compounding schedule, let's say money is compounded annually, well then N would be 1 because money would be compounded once a year. If money is compounded semi-annually, then N would be 2 because money is compounded twice a year. If money is compounded quarterly, N would be 4 because money would be compounded 4 times a year. And then monthly, N would be 12. And then if you have daily compounding, N would be 365 in most cases. Okay, so now let's take a look at what would happen if we had something called, this is what would happen if money was compounded during using one of these particular compounding schedules. Now there's another compound interest formula for the amount that investment's worth, assuming that N approaches infinity. Okay, now when N approaches infinity, I want you to think about, remember R over N, where R is some fixed number. If N goes to infinity, then R over N is going to approach 0. So keep that in mind. And also recall these two formulas that we had earlier. Either one of these limits will give you the number E. Okay, so to have continuous compounding, we're going to take this formula and we're going to let N go to infinity. So we're going to take the limit of this function as N goes to infinity. Okay, and that should be N in each case here, not X. So I didn't get that one corrected. Okay, so here you can factor the P out of the limit, and it would be just the limit of 1 plus R over N raised to the NT. Now, let's write NT as N over R times RT. Now, you can check that and see if you multiply it out on scratch paper that N over R times RT is the same as NT. And there's a reason I'm going to do that. Now, properties of exponents, since this is a product of these two factors, I can actually write this as this base here, 1 plus R over N, raised to the first factor, N over R, and then raised to the second factor, RT. Now trust me, I have a reason to do that. Okay, now when I do that, let's do a little substitution. So basically I'm taking the limit, I'm taking P times the limit of this expression. Now let's say that R over N is just X. So if R over N is X, then instead of 1 plus R over N, I have 1 plus X. And now 1 over X would actually be the same as N over R. So then I would have, for N over R here, I would actually could replace that with 1 over X. Okay, now something else, one last thing that we have to throw in here. Remember I said that as N goes to infinity, X goes to 0. Okay, so in other words, the R over N will go to 0. So basically what I can do is and say, well, over here I'm saying N goes to infinity. Well, that's going to be equivalent to saying X goes to 0. And then I still have my RT out here from here. Okay, now I know this is a little tricky, but let me just show you what I've written now. This part in here, forget the RT for now, but look at the part inside what I've enclosed here. The limit of 1 plus X raised to the 1 over X as X goes to 0 Well, that's up here. That's actually equal to e. So this part in this limit here is e, and so I have e to the RT, and then bring the p into it, and so I find out that with continuous compounding, the amount is actually the principal times e to the RT, and that leads me to this formula: A equals P to the times e to the RT if money is continuously compounded. And A is just the amount of the balance, P is the principal, R is the annual interest rate written in decimal form, and then T is the number of years. So now let's do two examples here, or two or three examples here. It says if $5,000 is invested at an annual interest rate of 3.9% for a period of 20 years, answer the following. Well, let's look what we know for now. We know that P is $5,000. We know that R in decimal is 0.039. And we know that T must be 20. Okay, so let's look at the first question. The first question says, if money is compounded annually, what will the balance be after 20 years? Well, if money is compounded annually, remember that means n equals 1. So I'm going to use this formula up here. I'm going to put 5,000 in for P. I'm going to put 0.039 in for R. I'm going to put 1 in for N, and I'm going to put 1 in for N up here and 20 in for T. So when I put all that together, I have 5,000 times 1 plus 0.039 over 1 raised to the 1 times 20, or just 20. And then I plug that into my calculator, and I get that money is worth $10,746.84. Now let's look at the second question. What if money is compounded monthly? Well, the only thing that will, for 20 years, the only thing that would change is that n would be 12. So if n is 12, then P is still 5,000, R is still 0.039, but now I divide this by 12, and out here I have 12 times 20 instead of 1 times 20. Or you could just go ahead and say that's 240. So I plug this into the calculator, and I get $10,893.57. And then finally, the third question says, if money is compounding continuously, what will the balance be after 20 years? Well, continuously means that I have to use this formula. And when I use this formula, I already know the principal is 5,000, and I know T is 20, and all I have to do is put in the rate R, which is 0.039. So I calculate 5,000, I get my calculator, and I figure out what is 5,000 e to the 0.039 times 20. And that gave me $10,907.36. Now you may have noticed that the value of the investment, the value of the balance, increased because we're actually compounding more and more on each time. On the first one we just compounded once a year. On the second one we compounded 12 times a year. But if you have continuous compounding, you're compounding an infinite number of times per year. Now the last thing I want to show you, or just give you some examples here, is make sure that you can calculate weird exponential expressions. So if you needed to calculate 2/3 raised to the square root of 11, make sure you can do that on your calculator and get the same answer I got, 0.261. Or for, let's say for some reason you needed to take pi and raise it to the e power, do that on your calculator and make sure that to round it to 3 decimals you get 22.459. Or if you wanted to evaluate this function with x equal negative 0.05, then that would give me 10 times e to the 1 minus negative 0.05, which would actually be 10 times e to the 1.05, because that's actually 1 plus 0.05 with the 2 minuses. And so then plug that in your calculator and get 28.577. And so we'll do some more examples later in this chapter, but for now I wanted to go ahead and introduce you with some calculations of exponential functions. And that's what these two are. They're actually two special types of exponential functions that we use in finance. So we'll move on to the next section now.